All right, so tonight's lesson, we got to do a little bit of backstory on this because we haven't tackled differential equations yet. But the lesson, and we're going to do it over 2 nights because these problems are kind of long. It's called exponential growth and decay. And so I've got some notes for you because there's a lot of word problems here. So I printed some stuff off before we went. So if you remember back to algebra 2, this should sound kind of familiar when you see directly proportional to. Remember, we did some problems, I don't know, at some point, direct proportion was y equals kx. Does that sound familiar? And then there was another type of variation called inverse, and that was y equals k over x and stuff like that. So we're going to kind of focus on this one, y equals kx. And when you read this, it says y is directly proportional to, but it's the rate of change of y is directly proportional to y. So the rate of change of y is dy dt. And when you say directly proportional to something, it's kind of like y equals kx, but now it's the rate of change of y is directly proportional to y. So this is kind of just some backstory, but so how differential equations work when we get to tackle them in a little while in AB. The gist of what we're going to be doing is, so if I say that we have dy dt is equal to ky. All right, when you go to solve a differential equation, our goal is going to be to split the variables up. So we're going to try to get everything. Now, this one's a little confusing because you don't see any t's, but I'm going to divide the y over. So this is going to be 1 over y dy. And I'm going to move the dt over. So that's going to be equal to k dt. And we're going to integrate both sides. So the overarching goal here when you do a differential equation is it's going to be to split the variables up so that you got them on matching sides. Now, k is just a constant in this problem. So when you integrate with respect to t, think about what that's going to give you. Okay, so if we integrate both sides here, 1 over y, there's 3 big ones, 1 over x, 1 over y, 1 over u. Those all result in natural log. So that's natural log of y is equal to, now remember, k just stands for some number. So if some number gets integrated, it's going to be some number variable. And what's the variable we're working with is t. So this is going to be kt plus c. All right, so now somebody should have a question, and that question that somebody out there should have is, well, why did we only do 1 plus c? You're integrated on both sides. So technically, yes, you could definitely do a plus c on either side. In terms of the notation, though, plus c just stands for any number that's out there. So putting a plus c on both sides kind of becomes redundant almost because we don't know what the number is anyways. So in terms of the notation in calculus books and stuff, the plus c only lands on the right side of a differential equation. And then from here, we got to do some logarithm manipulation. So this is where there's usually some questions. So we need to know that natural log is the same thing as a logarithm in base e. So we're going to call this log ey is equal to kt plus c. And from there, what do we know about logarithms? We should know the phrase log base answer equals exponent. So this right here should be our thought bubble. Log base answer equals exponent. So the base of this is base e. The exponent of this is kt plus c. And then what's left, the answer, is y. Okay, we're getting there. So now if we wanted to simplify this a little bit, We could say that this is e to the kt e to the c is equal to y. Think about your properties of exponents, right? If you have, so in other words, let's say this. If you have a to the b plus c, that's the same thing as a to the b, a to the c. Because when these are side by side, we just add these up, right? So same deal here. That's just a different way of writing this. All right, now e to the c, this whole thing is really just a constant. So we can say that y is equal to, we're going to change that to just a constant, and that's going to be c e to the k t. Your must know formula is y is equal to c e to the k t. Now, you do not have to replicate what we just did. I wanted to give you a little bit of backstory on some differential equation maneuvering because we're going to be doing some stuff like that in these problems. The one we just did, though, you don't particularly have to replicate that. You just need to know this formula. And this formula is going to be the exponential growth or decay formula. So before I go any further into some example problems of what we're actually going to be using this for, do you guys have any questions there?
Could you repeat again how the C, the situation with the C?
So e to the c, this whole thing is just because we don't know what c is. C could be anything. So this whole thing can just be condensed into just a constant because it's still just a number and we don't know what that number is. So whether it's e to some random number or just some random number, it still falls under the category of just some number. So that's why we can just condense it into c. So, and then e to the kt, that's an actual variable up there. So,
Yeah, thank you.
In terms of at the very beginning, when you're doing ky is equal to dy over dt, k is just a constant.
Yes.
But what is that actually saying how does that relate to exponential growth and decay? Like as
So hold that thought. I think it'll help if we start to do a problem or two and maybe it'll click a little more. So let's try one. And then if it doesn't, we'll circle back. So I printed these out earlier for you guys so that you can copy them down and you're not sitting here watching me write forever. Okay, so let's have you go ahead and copy that into your notebook. I'll stay quiet for a second. And this will be our first example. So it says the rate of change of y is directly proportional to y. When t equals 0, y equals 2. When t equals 2, y equals 4. Find y when t equals 3. So these are literally just the calculus version of an old algebra 2 problem you used to do. In algebra 2, we used to do direct variation. This is just the calculus spin on an older problem from a couple of years ago. So when we hear the rate of change of something is directly proportional to something, we're going to go ahead and use this formula. So when we start this off, we're going to be starting with y is equal to CE to the KT. Okay. And we're just going to kind of go through and just break this down piece by piece. So the first piece they give me is right here that I just underlined. That's all we're working with. When t equals 0, y equals 2. Let's work with that. When t equals 0, y is 2. So if y is 2, that's going to be CE to the k times 0. Okay, so this is really CE to the 0. And e to the 0 is equal to 1. So that tells us that C is equal to 2. Okay, so that's a good start. All right, so now when we're looking at this formula, we now know that C is equal to 2. All right, so now we want to keep going. What's the next piece of information? So for this first piece, we were using y equals 2, t equals 0. That's what we did up here. Okay, so we're going to keep going. What's the next thing they tell us? When t equals 2, y equals 4. Okay, so now we have that same formula. Y equals CE to the KT, except what do we know about C now? Now in this version of it, we know that C is equal to 2. And now when we plug in, what are we plugging in? T equals 2, y equals 4. So when y equals 4, t is 2. So if t is 2, that's going to be 2k. Okay. Okay, so if we want to go through and do some solving now, we're going to try to solve this for k. First step, I'm going to divide both sides by 2. So this is 2 is equal to e to the 2k. All right, we're trying to solve for k. So we need to know some more logarithm properties. Does anybody out there have a strategy or know a logarithm property that we could employ here to solve for k?
Use like the logarithmic power rule to just bring it down in front.
So what are you trying to do?
Just apply natural log to both
Yeah,
sides.
okay, there you go. That's what I want to hear. Yeah, apply natural log to both sides, correct. So if you natural log both sides, that's going to be natural log of 2 is equal to natural log of e to the 2k. And now you need to know a rule. Natural log of e to the stuff is the stuff. There's 3 main natural log rules that you need to be aware of. Natural log of 1 is equal to 0. Natural log of e to the stuff is the stuff. And e raised to the natural log of the stuff is the stuff. So these 3 rules come in very, very, very handy when you're doing differential equations and exponential growth. Natural log of 1 is 0. Natural log of e to the whatever is the whatever. And e to the natural log of whatever is the whatever. Okay, so with that in mind, this is going to be natural log of 2 is equal to natural log of e to the stuff is the stuff. Okay, and we're going to solve this out for k. So I'm going to divide both sides by 2. Now, there's some more playing around we can do with this. All right, so there's nothing wrong with that answer, but we can make it a little better. So would you agree that this is the same thing as saying 1/2 natural log 2? Same thing, right? K is just ln over 2 is half natural log 2. Okay, we need to know a logarithm rule. Whenever you have a number in front of a logarithm, so like if I have natural log of, I don't know, whatever, we'll just say b, and I have an a out front. This is the same thing as natural log of b raised to the a power. That's one of your logarithm properties. A number in front of a logarithm is actually a power, okay? So this is really natural log of 2 to the half, or what we kind of want you to get to here is that k is equal to natural log square root of 2. All right. Any questions up to that point? All right. Well, now when we read the question, there's only one thing left. This is what they're actually asking us to figure out in the question. Here's the answer to the question. Find y when t is 3. Okay, so we're going to start from scratch all over again. Y equals c e to the k t. But now, what have we solved as we've gone through this? This question is saying now, find y when t is equal to 3. Now, so we're going to find y, but for c, we've already solved for c. C is 2. E is e. We just figured out that k is the natural log of radical 2. And it tells us in the problem that this is 3. Okay, so we now have, we can write that a little nicer. We can say y is equal to 2e to the 3 natural log root 2. You could also write it as, that's being a third power. You could do other things with that. So here's where our discussion kind of wraps up. If this question was in the non-calculator section, that's it. That would be your answer. We would pretty much just kind of stop there. If this landed in the calculator section, they might have you type this in. And I have that answer already for you guys just in case. So that would be the same thing as approximately 5.657. Means the same thing if you just typed it into a calculator. So either or, just depending where this question was asked and what choices you had, would be acceptable. Do we have any questions on that one? Okay, so if that makes sense, that's pretty much the idea. Now, just some of the problems we have are going to kind of veer off and be a little crazier with what they're talking about, but the process is the same. We just have to kind of translate what the question is asking and then assign the variables accordingly. So what did we do here? We looked at the problem and we said, okay, first things first, you got to know that formula or you're pretty much done before you start, right? So the must know formula for this is y equals ce to the kt. And then from there, just start at the beginning, plug in what they give you and solve for the thing that you can, and then do it again. And then at the end, this is the thing we're actually looking for. Okay. All right, let's look at example 2. All right, so this one is the same kind of problem, just with a whole bunch of gigantic, messy words and things, but it's going to be the same idea. So I will stay quiet for a solid 60 seconds here and let you guys copy this down.
How many years after like the current standpoint at it's already decayed to 7.5, or like how many years total?
So what we have to figure out here is that when you start this question, it's still going to be the same formula. Y is equal to C E to the K T, but we're going to alter this. And instead of Y equals, it's still going to be that when we read this up here, suppose that 15 grams of a cesium isotope was released during an incident. Okay, it is known that after 30 years, 15 grams of K to this, however, you cannot drink the water. I'm reading this myself right now. Hold on. Okay, so what I would do with this is I would change this to A equals, because what are we talking about? Now we have something specific here. And A is going to stand for amount. You don't have to use Y equals. We can pick another letter if it helps us remember what's going on. So I'm going to say the amount of whatever it is I'm talking about is going to either be growing or shrinking, whichever way that they have it written here. So
For what it's asking for, is it asking for like the total number of years of decay or like after the 30 years?
let's see. I'm reading this right along with you. It's been a minute since I've read this. Hold on, let me see. So I'm just picking out pieces as we go here. So I see that the amount is 15 when this is the original, right? So when 15 grams is released, that's like T equals 0. You agree with that? That's like our intro. And then it says it's known that after 30 years, so that's going to be our first step. And then after 30 years, that's T equals 0, then the amount is going to be 7.5, and we'll do some math with that. And then finally, it's going to say when it's at 1, so when the amount is equal to 1, how many years will it take for this to occur? So what this question is saying is from the beginning of my story, which is at T equals 0, how many years is it going to take for the water to be safe? So at T equals 0, there's an accident. How many years from the accident does it take for the water to be safe? And for the water to be safe, you need the amount of whatever this stuff is to be at 1 or less. Does that make sense?
Yeah.
Okay. So if we go through this, I kind of like as a strategy, because like you kind of seen whenever you were asking me questions, I was also like, I don't know, let's read. So a good strategy here is kind of go off to the side and pick out all the different things you have. So like we can see right at the beginning, okay, T equals 0, that's when the accident happened. When the accident happened, here's the amount that we had. And then the next piece they tell you is that after 30 years, it's the amount has decayed to 7.5 from the 15. Okay, finally, we need the amount to be at 1. How many years is that going to take to where we're at a safe place? Okay, so we kind of can just go off to the side and map that out. And now we need to just go through and actually crank out the math. So, yeah.
And I can jump in. So the wording of how it says in those 30 years where it says it is known is like saying that it hasn't happened yet. It's just saying that they know that in 30 years. So if you're thinking that like T equals 0 is the 30 years, it's not because it says it is known. If that makes sense. I don't know. That's how I thought of it. I had the same question.
It's known that after 30 years, the 15 grams have decayed to 7.5. So for me, the way I read this is that like this piece right here that I'm putting brackets. Oh, you can't see that, sorry. The part that I just put brackets around from here to here, the way I interpreted it is like this is present day. So like I'm telling you the story as of right now, it's been 30 years and here's my results. But we can't drink the water until we get to 1. So the way I'm reading this is like in between here is like that's today, that's what I know. Here's where this mess started. Here's where I'm at right now. And I want to know how long is it going to take till we get to where they want us to be. Does that make sense?
So they are asking how long is it gonna take after those 30 years?
No, how long in I'm reading this as how long in general, because we're going to be starting at t equals 0. So even though we're at 30 right now, how many years will it take until the water is safe to drink from the beginning of the story? So from
Right,
t
from,
equal,
okay, yeah.
yeah, so from like the time of the accident to however many years is basically what they're asking. Okay. Okay, so let's get to it and see what we can come up with. So I'm going to plug in 15 for A. And that would be equal to CE. When I put a 0 in for T, that's going to be 0. And then so that's 15 is equal to anything to the 0 is 1. So that should tell us that C is equal to 15. Okay, so now when we start with that, now we're going to say, all right, A is equal to CE to the KT. We'll replace C with 15. And now we're going to use our 7.5 and our 30. So if A is 7.5, 7.5 is equal to 15 E. Now we're going to let T be 30. So that's 30K. Okay, divide the 15 over, and 7.5 divided by 15 is a half. So a half equals E raised to the 30K. Same deal, we should natural log both sides. So natural log of a half is equal to 30K. So if I would divide both sides by 30, I'm going to represent that as 1/30th natural log of 1/2 is equal to K. And not much else we can do with that. So let's go through and use our last piece of information. And that's going to be when the amount is 1. So this would be amount is equal to CE to the KT. So we'll plug in everything we know. A is 1. From up above, we know C is 15. E raised to the, we know what K is, and we want to solve for T. So this is 1/30 natural log of a half. And we've got a T back there. So now whenever we solve this for T, that should get us to an answer. So first thing I'm going to do is divide both sides by 15. So this is 1/15 is equal to the E raised to this stuff. Okay, and we got a natural log this again. So this is going to be natural log of 1/15 is equal to natural log of 1. See, where does that give us? We need natural log that side. Natural log of e to the stuff is the stuff. So the stuff is 1/30. I didn't need a natural log there. 1/30 natural log of a half times t. Okay, you guys still good? Am I going too fast? Are we still on the same page? All right, and we're trying to solve for t. So all you have to do is just divide that mess over. So this, I'll go up here with it. So this would be, if we divide that over, this would be natural log of 1/15 divided by 1/30 natural log to the 1/2. And we have in fact solved for t. Now, that answer doesn't do us a whole lot of good in terms of like, well, what does that mean? So I'm pretty sure this would probably land in like a calculator kind of question. And if you fired all of that into a calculator, it would come out to be that T was approximately, if we were rounding, equal to 117 years roughly. So do we have any questions there?
What's the difference between using the absolute value?
When you were solving, oh, sorry, you can go.
Go ahead, Ray, and then Jake,
I
you're
was
next.
gonna say, what's the difference between using the absolute value symbols for ln and not?
So absolute value symbols for ln are only when you integrate. So the deal is that technically natural log is never negative. So like when you think about natural log, if I say natural log x is the same thing as a logarithm in base e. So when you have a log in base e, just think about the number. So log base e x equals something. So this would be e to the something is equal to x. And no matter what I raise e to, I could raise e to a positive number. I could raise e to 0, and I could raise e to a negative number. And regardless of which one of those things you pick, the outcome is guaranteed to be positive. E to anything positive is positive. E to the 0 is 1. And e to a negative, if I do e to the negative 4, that's just 1 over e to the 4, which is still positive. So in other words, anytime you integrate 1 over x and 1 over u, 1 over y, stuff like that, and you get natural log, it's just kind of a math technicality that you put those absolute value symbols around it to signify that, hey, this has to be positive. Whereas when you're just working with natural log, normally you're not required to do that. So the only time that you have to throw those in is when you integrate and backtrack into natural log. Jake?
Yeah, I was just wondering when you were solving for K, how'd you know to stop there and not like keep going like you did in the last question?
When I solve for K, not to Q. Yeah, I mean, so you could have, right? There's nothing. The only reason I kept going in the previous question is because I saw that it was a power of 1/2, and 1/2 is the square root power. So I mean, yeah, technically, there's nothing wrong if you had stopped right there. There's nothing wrong with that. This would just kind of boil down to what answer was listed in multiple choice and making it match up. So typically, if you see like the 1/2 power, they're going to jump and use the square root, or the 1/3 power, they'll probably jump and use the cube root. Whereas 1/30th, usually nobody's writing that as the 30th root. That's kind of weird. That doesn't make it wrong though. So like if you wanted to, you could have said that it was K was equal to natural log of the 30th root of 1/2. That would produce the same answer. There's nothing wrong with that. Typically though, if it's just like half or third, square root and cube root are real common. So I'm just trying to keep it with what they would probably do in multiple choice. In this question, I don't really think it would matter because I'm pretty sure this would be a calculator question because they wouldn't leave that as an answer choice. That's too obscure. Nobody would know what that really meant. Does that make sense?
Yeah, that makes sense. Thanks.
Okay. Any other questions out there? All right, so we are going to try one more of these. So if you looked at the schedule that I posted on Canvas, I kind of figured this was going to take a while. I have like 5, 6, at least 6, I think, versions of these questions. Some of it is free response as well from previous things. So I kind of figured we were going to need 2 nights to really get through all of these. And that looks to be about on schedule. So let's take a look. We'll wrap tonight up with, I'll put this one up there and we'll talk through it for a second. And then I'm going to give you guys about, I don't know, 7 or 8 minutes or so to work through it. And then we'll get a solution posted and that'll wrap up tonight's class. And then on Thursday, we will pick up from here, do some more review on this, and then jump into a free response question as well that tackles this. So go ahead and copy this down and then we'll talk. Okay, so this one has a twist on it, actually. So before I let you go on your own, we're gonna have to do a little bit of talking here. What can you tell me about the previous problems that we had done? An example. The paper here. An example 1 and 2. Did you notice that they gave you the same thing both times? In example 1, we had t equals 0. We had that initial condition of t equals 0. And in the second condition, we also had that initial condition of t equals 0. When the amount was 15, what we had the time equals 0. Whereas in this question, I don't see anything on here that says at t equals 0. More specifically, this one's having us work backwards to figure out what t equals 0's amount is. So it says a graduate student is studying a population of fruit flies. They work under the premise that the exponential population increases according to the law of exponential growth. So as soon as you hear anything about exponential growth or decay, that's this lesson. If 100 flies were counted after the second day, pause, and just draw some brackets around that. So we know right away that if 100 flies were counted after the second day, that's t equals 2, and the amount was 100. And then we also know that 300 were counted after the fourth day. So 300 were counted after the fourth day. All right, how many flies were counted? So that's going to be the amount when t is equal to 0. Okay, so that's the information that we should be able to pull out of the opening thing. But again, this is a twist in this because they don't give us the initial condition, which means it's going to be harder to solve. So here, check this out. Like if you go through and you start to try and solve, I'm going to write underneath this on a piece of white paper. So what do we know? Amount is equal to CE to the KT. Okay, so if you just plug in 100 for amount at t equals 2, okay, we got a problem here. And that's, well, I see multiple variables and we can't solve for multiple variables at this point at the same time. Whereas whenever t was equal to 0 and all these other questions, they gave us an amount at t equals 0 that got rid of the k. And then we were able to just say, oh, okay, yeah, this is equal to c and we're good. Does that make sense that this is different now whenever you don't have t equals 0 given to you? So we need to get creative here and come up with a different way. So it's still going to be A is equal to CE to the KT. That's not going to change. Any ideas? We have a Zoom full of smart people out there. Do we have any creative ideas we could try?
Would you do system of equations?
I don't hate that idea. What did you have in mind? So that sounds similar to what I did. I don't know that I would call my work a system of equations, but I think we're on the same page, same train of thought. What are you thinking?
Well, you kind of set up both simultaneously and then you kind of solve them together.
Okay, so what would you set up for me? Tell me the first thing you would say.
The first one would just be what we just had, which is 300 is equal to CE to the K2.
All right, C 300 is equal to, so if we did the 300 one, that's going to be C, E, and then T is 4, right? So that would be 4K, right?
Oh, yeah, sorry.
And then if we did, yeah, you got the right idea though. And if we do the other one, let's do the same deal. The other one side by side would be 100 is equal to CE to the 2K, right?
Yeah.
Okay.
And then you kind of put both of them into the logarithm form.
Yeah. So what I was thinking is that think of it this way. In the first two problems that we did, here's going back to that cesium problem. What was the first thing we solved for?
C.
Yeah, and when we did the first example, what was the first thing? The thing you solve for every time when t is equal to 0, the thing that you keep solving for very quickly is c. So to me, I think we should figure out the way to quickly solve for c. So if you go on the left side, 100 divided by e to the 2k is equal to c. And at the same time over here, 300 divided by e to the 4k would be equal to c, right? So now here's where, when you said system of equations, that kind of checked out in my brain. By solving both of them, now we're able to say, okay, this thing is equal to c, and this thing is equal to c. So what connection should we be able to make here?
Set them equal to each other.
That's what I was thinking. So if we would take these two ideas, if they're both equal to c, that means they both should be equal to each other. So 100 over e to the 2k is equal to 300 over e to the 4k. And if we're going to solve that, we would solve that by cross multiplying. So this would be 100 e to the 4k is equal to 300 e to the 2k. And then I would divide maybe that 100 over. So then we could say e to the 4k is equal to 3e to the 2k. Maybe divide the e's over. E to the 4k over e to the 2k is equal to 3. Well, what can you tell me about just exponents here? E to the 4k over e to the 2k. What do we know about variables? If you have x to the a over x to the b, and you simplify those, that should be x to the a minus b, right? So same deal here. This would then be e to the 2k is equal to 3. Okay, so then what are we going to do with that? Well, we probably should do some natural log stuff now. We can say natural log of both sides. So that's natural log of e to the stuff is the stuff. So 2k is equal to natural log 3. And then does that make sense that when we divide by 2, natural log of that over 2 is really going to be natural log of the square root of 3? Because that's really a half out front, which turns that to a square root. If that step doesn't make sense, that's really k is equal to natural log of 3 over 2, which is a half natural log 3, which makes that square root of 3. Okay, so now you know that k is equal to natural log of 3. Okay, so I'm going to stay quiet for a minute. I want you guys to kind of work from there, see what you can come up with. So that was the hard piece, was going through that where you had to start without knowing the initial condition. So keep going, keep reading through the question, see what you can come up with. We'll talk in a couple minutes. Okay, so where does that take us to? A is equal to CE to the KT. So I'll put the T out front here, and because we know K is going to be natural log radical 3. So now we can go through and grab the first ordered pair of amount is 100 CE, and this is going to be when T is 2. So 2 natural log root 3. And then if you go through and solve for C, this is 100 over E 2 natural log root 3 is equal to C. And if you did that in a calculator, that gives you pretty much 33.3 repeating. So that gives you your C value. So then if you start over, this is going to be A is equal to C. So 33 and a third, or 33.3 repeating, E. And then we know this is going to be T, and then K is natural log root 3. So the A and the T are always changing based on which part of the problem you're in. C and K, these kind of get locked in. So now for the last piece, what are we trying to figure out? We're trying to, in this particular question, we're trying to figure out what was the amount of flies at T equals 0. So to figure this out, we need to plug in 0 for T. So A is equal to 33.3 repeating E to the 0 times that. Well, 0 times anything is going to be 0. So this is A is equal to 33.3 e to the 0. E to the 0 is equal to 1. So the answer to this question is A is approximately equal to 33 flies at T equals 0. So now I rounded to the nearest fly because you can't have a third of them. So that's how I came up with 33. Yeah, so does anybody have any questions on that?
When you were solving for C,
Mm-hmm.
you wouldn't have to plug that in the calculator, would you? Because because 2 natural log square root 3 would become natural log 3, and then the E and the natural log would cancel out, so you would just get 100 over 3.
I don't disagree with that logic. That looks pretty good to me. Everything, yeah, that's good what you just said. A lot of these are calculator, but yeah, what you just said, real good. Let's recap what she just said. So this is 100 over E to the natural log 3, because this power here 2 really means to square that radical. So that will drop the radical. And then this is one of our logarithm rules. E to the natural log of the stuff is the stuff. So that's 100 over 3. And 100 divided by 3 gives us that 33.3. Yeah, that's a real good pickup on that. That is correct. And I don't know if we needed a calculator anywhere else on here. Yeah, I like that. Very good. Any other questions, comments, thoughts on our introduction to exponential growth and decay? Okay, so hold on, we have something in chat. If this is an FRQ and is graded to the work, does the accuracy graded to the work? Does the repeating line matter? Well, I mean, technically, you're supposed to do 3 decimals at all times. So in this case, we would need some more specific instructions. So this would still land under the multiple choice category of questions, I feel like. When we get to what free response looks like, let me dig it up here, I'll show you. And we'll go over some next class. So here, like this one is our free response one we'll hit on Thursday. So whenever you do one of these, it's free response. It's going to have a part A, a part B, a part C, stuff like that. So on Thursday, we'll go over all of that. So I got like 2 more questions that are very similar to what we did tonight, and then we'll do the free response question on Thursday. Okay. So if you guys don't have any other questions, I will head off with the record here and turn it off, and I'll have it uploaded in 5-10 minutes. In terms of the AB stuff, if you guys have any questions, feel free to come in to advisory tomorrow. Come in after school on Wednesday. I'll do a session 2. So if you want to come practice, those are 2 sessions that are available. And then in terms of the BC stuff, I will see you guys Thursday night at 8:30. So have a good night. Thanks for coming.
Thank you.
You're welcome.
Thank you.